Welcome to Bassmaster, friends. In my last video on Advanced Engineering Mathematics by Erwin Kreyszig, I had solved problem set 1.5 from the book which is available on the internet. And in this video, I am going to take few more problems from this book and looking at problem set number 1.6, what I find is this set of problem is mostly theoretical, and we will have not much to solve and show the results in this, and so is the case with problem set number 1.7. So what I will do is in this I will take you to a straightforward chapter 1 review questions and problems. There are few problems there which we can solve. Few of them there are also theoretical questions, but here if we look question set from 17 to 21 from here to here, and then from 22 to 26, which are actually initial value problems. I will take all these questions, total of 10 in this video. And interestingly, we will also touch the modeling question in this video. There are 4 modeling questions which has been given in this book, and we will take all 4 of them. Okay. Now, let us start from question number 17, which is depicted here, and start solving them. Before I move ahead and solve these problems for you, I would like to request all my viewers who have not subscribed to my channel to subscribe the channel and hit the like button if you liked the video. And if you have any question, please feel free to ask on the comment box, and I will be happy to reply to your queries. Thanks a lot once again for joining. So watch the video ahead in order to see the solution of these problems. Okay. So let us solve this problem, which is actually first problem. It is quite simple. We have to find an integrating factor in this and resolve this. Okay. And integrating factor for this will be actually nothing but if is equal to E, and this is 2.5 dx E, this will be 5x oblique 2. This is the integrating factor. Therefore, we can write the above equation as the one which is I am writing here. At this place, undoubtedly we need to use by parts to solve this, and using that normal method, we will assume u as x and dv is equal to e to the power 5x oblique 2, and this will give us nothing but du is equal to dx and v is equal to, okay, we know is the formula which is used for by parts. Therefore, we will use this particular formula to solve this. So we have x this much. Here we take uv, which will be 2x oblique 5, 5x oblique 2 minus v will be 2 oblique 5, and du will be nothing but dx, and this will give us nothing but 2 oblique 5x 5 oblique 2, and then again this will be divided by 5 oblique 2, which means there will be a square of this, or 4 oblique 25. So I write it directly 4 oblique 25 e to the power 5x oblique 2. Okay, this will be the value of this one. Therefore, our solution will be 1.6 and 2.5 and this is nothing but 8 oblique 5 is 2 oblique 5 x 5x oblique 2 minus 4 25 8 is to 5 plus c, or y is equal to plus c e to the power minus of 5x oblique 2. So this is going to be the general solution of this particular problem, okay? And this will not be e to the power 5. Actually, this the entire expression, if we divide with e to the power 5x oblique 2, here it will just y. Here this will also strike it down, and this will strike it down, and here it will come c oblique e to the power 5 oblique 2. When we take it on the upper side or on the numerator, it will become e to the power minus 5x oblique 2. So friends, second question let us attempt, okay? Second question is exactly as the first one. We have to again find integrating factor and resolve this. And integrating factor here will be e to the power integral of minus 4 minus 0.4 dx, or this will be e to the power minus 0.4 x, okay? Therefore we can write it y e to the power minus 0.4 x x, or y e to the power minus 429 sine x e to the power minus 4x dx plus c, okay? Now this one will be little lengthier. This one will be little lengthier because we need to apply integration by parts multiple times to get our answer, and you have to see how we do it, because both sine x and exponential, these are non-vanishing. I mean, every time we differentiate sine, it will give a cos, and every time we differentiate a cos, it will give us a sine. So we need to wisely assume and do the integration by parts. So here what I'll do, I'll take sine x e to the power minus 4x dx plus c and assume this is equal to I is equal to integral of sine x, and so far as assumption of u and dv is concerned, we will assume sine, which is actually a trigonometric function, as u sine x, and dv we will assume as 4x. This will give us dy is equal to cos dx, and v will be just integration of this will be nothing but e to the power minus 0.4 divided by minus of 0.4, and this will become minus 5 divided by 2 e to the power minus 0.4, sorry. So in the first iteration, what we will get, as per the by parts, we have u dv is equal to uv minus v du. So here we have u here and v here. So our first part will be sine x multiplied by minus of 5 oblique 2 e to the power minus of 0.4x, and this will become v, which is nothing but minus of 5 oblique 2 e to the power 0.4x, and du, which comes from here, which is actually cos x dx. And this will become minus of 5 oblique 2 sine x e to the power minus of 0.4x plus 5 oblique 2 cos x e to the power minus 0.2. Now again we apply this one here. I'll pick up a different color for you to understand better. Now I will assume u this and dv this. The u we have cos x, and dv we have e to the power minus 4x. This will give us dv is equal to minus sine x, and v is equal to, again same process here, this minus 5 oblique 2 4x, which equal to uv. This will be cos x is 2 minus of 5 oblique 2 x minus v du. V is this and du is this. So finally we have, this will be actually integral sign here. This will be dx. I is equal to minus 5 cos x e to the power minus of 25 oblique 4. So we have reached at this place where our integral, this one is coming to be this, where this is actually an integration. Okay, therefore from the previous step we get minus 5 oblique 2 sin x e to the power minus 4x minus of 25 oblique 4 cos x 4x. From previous steps we will get this particular expression that we have, and now if we compare the I what we have assumed earlier, we have nothing but I here 1 and 1 I we have at this place. So actually we can write I is equal to 5 oblique 2 minus sin x e to the power minus 4x minus 25 oblique 4 cos x e to the power minus 0.4x, then 25 oblique 4i, and let us take this particular thing on the left hand side here and add it. It will become 29 oblique 25i is equal to cos x, and therefore our solution will be I. The entire thing will be multiplied with 25 oblique 29. So 25 oblique 29 is 2 minus, I'll take it out, then I can write 5 oblique 2 sin x 0.4x plus cos x e to the 4x. Plus we can, if we wish, here we actually we should have written a plus c. Here also we can write a constant of integration plus c. So you can just check the answer for this. This will be the answer for this particular solution. So let us move to the next question now. So friends, let us move to the next question, and we have come to question number 19. And okay, this question is not at all very difficult. This is a variable separable question. Okay, and we can do it very easily. First of all, what I'll do, I'll write 25y and this y prime as dy oblique dx, and this 4x I'll take on the right hand side of 0, and then I will separate with the variable. I will write y dy, and here I'll write 4x dx. Now if we integrate on both sides, this will become 25y square plus divided by 2, not plus, sorry, and this will become 4x square divided by 2 plus a sign of constant or integration constant here. This will become simply 25y square minus 4x square plus a constant c1, and c1 is purely a constant, which is in this case, since we have assumed a constant c, when we multiply the entire expression with 2, this will become twice of that. I have assumed a different constant which will be nothing but it will be twice of c, and that will be c1. For the sake of writing, you can also write 25y square minus 4x square is equal to c. This is perfectly alright. This is the answer. So let us move to the next question now. This is the question, friends, question number 20. If I can write this as dy oblique dx a y plus by square, or dy oblique dx is equal to y, and then we can do a variable separation for this. I will bring entire expression of y on the left hand side in the denominator and write as and then dx. Now we can use partial fraction decomposition in order to separate this. Let me assume 1 oblique y a plus by is equal to a oblique y plus b upon a plus by. Now, if we compare denominator with denominator and numerator with numerator, we have a plus b of capital B y is equal to 1. So this is a constant term, there is no variable, which means the variable is 0. That means this particular expression will be 0 and this will be 1. From here we get a capital A is equal to 1 and b capital A plus capital B is equal to 0. From here we get capital A is equal to 1 oblique small a, and from here we get capital B is equal to minus a small b of capital A. A small b is to capital A, okay, and that capital A I can get it from here as 1 oblique, and this will give me minus b oblique a. Then what shall we do? We need to substitute this a, which is this one, at this place, and b, which is this one, at this place. Okay, we have, okay, it means dy we can write as dy here. Therefore we have 1 oblique a dy oblique y minus b oblique a b upon a dy oblique a plus by is equal to dx. Now we apply integration on both sides. Okay, here we will have 1 oblique a ln y, here we will have b upon a. 1 oblique b is to ln a plus b is equal to x plus a constant of integration c. This will be 1 oblique a ln y minus ln a plus by is equal to x plus c. Okay, 1 oblique a ln y oblique a plus by x plus c. This will become ln a plus by is equal to ax plus ac. Now we can take an anti-log of this, and while we take anti-log of this, actually what will become we will have y a plus by here, and this will become e to the power this much. So this is e to the power ax plus ac, which we can write as e to the power ax multiplied by e to the power ac. And looking at this here, this is constant, and at this place this is also a constant, but different from this one. So we can assume a different constant c1. Therefore we can write y a plus by is equal to c1 e to the power ax, and then y is equal to a plus by multiply with c1 e to the power ax. This will give a c1 e to the power ax plus b c1 y e to the power ax. Now if we take y together, we will have y minus bc1 y e to the power ax is equal to ac1 e to the power ax. Now for the sake of convenience, we can assume bc1 and ac1 as two different constant. I will assume this particular one was k and write e to the power ax, and this particular thing I will assume c2 and write at e to the power ax. Then our case becomes y is equal to 1 minus k e to the power a x is equal to c2 e to the power ax. This will give us nothing but y is equal to c2 e to the power ax divided by 1 minus k e to the power ax. And this will be the solution of the given problem. Right friends, so let us move to the next question, which is question number 21. Question number 21 is also going to use a different concept. So we will use a new concept to solve that. So let us discuss that concept. So friends, we have reached to the last question of the section general solution, question number 21. This is a very interesting question that we will be solving in this particular video. This is actually the non-homogeneous differential equation which is in the form of m dx plus n dy is equal to 0, and we need to actually find out integrating factor for finding a solution of this particular problem. Okay, and before we find integrating factor, we need to actually find out whether this particular equation is exact or not exact. Okay, if it is exact, then our task will become much simpler and we can quickly solve the problem. But if it is not exact, then we need to find integrating factor and apply other methods to solve it. Okay, if we compare this equation, we find that m is equal to 3x e to the power y plus 2y and n is equal to x square e to the power y plus x. Now, if it is exact, then delta of m oblique delta of y is equal to delta of n oblique delta of x will hold true. Let us find delta m oblique delta y is 3x e to the power y plus 2 and delta n oblique delta x is 2x e to the power y plus 1. These are not equal. Okay, this means this is not an, since dm oblique delta y is not equal to delta n oblique delta x, this is not exact. Now we need to go one more step forward to find the integrating factor, and the rule to find the integrating factor for this kind of equation is, first of all, we will find mu, and if will be nothing but e to the power mu dx, and we need to find mu in terms of variable x. This will be 1 oblique n here delta y minus delta n delta x. N is this, m is this, and we have 1 oblique x square e to the power y plus x, and then delta m minus this. This minus this will be nothing but this minus this, which is 3x e to the power y plus 2 minus of 2x e to the power y minus 1, and this will give us x e to the power y plus 1. Now if we just take x common in the denominator, okay, this and this will go off and we will have 1 oblique x. Therefore, integrating factor will be e to the power 1 oblique x dx, and this will be nothing but e to the power ln x. This will give us x. So we have got a very simple integrating factor for this equation, which is just x. So the rule says if we multiply this equation with integrating factor if, okay, this will become actually exact and we can integrate it quickly. So our given problem is 3x e to the power y plus 2y dx, 2y and then here dx, we will multiply with x here. Similarly, we will multiply x and write x square e to the power y plus x dy. One more thing I wanted to tell you, that once this equation become exact, even the partial integration will actually give us an answer. So we need not do this one, or if we are doing this, we may leave this one. Okay, so which means if we integrate just this portion of the equation, we will be actually getting our answer. Okay, but I'm doing it full for you here for you to understand. Okay, so we have 3x square e to the power y plus 2xy dx plus x cube e to the power y plus x square dy. Now we can open it and we can write all separately without any problem. Apply integration on both the sides, here and here. On the right hand side, this 0 will become a constant and this will become 3 oblique x cube oblique 3 e to the power y plus 2 x square oblique 2 y plus x cube e to the power y plus x square. No, sorry, this is not cube. This is dy. This will remain as it is, okay? X cube y, right, it is correct. And this is nothing but x square y is equal to c. So this gives us 2x cube e to the power y plus x square y plus x, not 2. This is just, what am I doing? This is 3 is cancelled out. We have only x cube e to the power y, x square y, plus here we have x cube e to the power y. This y will not be there because since this is exponential, the integration will give us just ey. Here this y will be here, so this is correct. Plus x square y is equal to c. So you can see that we have 2x cube e to the power y plus we have 2x square y is equal to c. If we divide the entire expression, right hand side may still be a constant. I will assume as a c1, and left hand side will become x cube e to the power y plus 2 plus x square y is equal to c1. This is the solution, general solution of this particular problem. Okay? And one general solution usually we write is the integration is equal to c, which is nothing but left hand side is equal to a constant on the right hand side. The correct worked out solution for the given problem is right in the box. Okay, so we will move to initial value problems now, and till here I would like to thank you for patiently watching my videos. If you like the video, don't hesitate to hit like and subscribe button. Okay. So let us move to question number 22 now. So friends, we move to our next question, and this question is question number 22 and is an initial value problem IVP. Okay. In initial value problem, we use the given conditions to find the constants which we have been using in a general solution. Okay, this is quite simple. We have to, this equation is in the form of Bernoulli's equation. Okay, so we can use integrating factor to find the solution, and the integrating factor will be 4x dx or e to the power 4x square oblique 2 or e to the power 2x square. This is the integrating factor. So while we apply the integrating factor, we can write above equation as e to the power 2x square y, then this side 2x square is to the power plus 2x square. This will give us minus 2x square plus 2x square is equal to e to the power 0, or this will become 1. This will give us, when we apply integration on both the sides, we will get e to the power 2x square y is equal to x plus a constant of integration c. Okay, and we have been given initial value condition, which actually says that x is equal to 0, the value of y will be minus 4.3. So we can substitute at the place x0 and at the place of y minus 4.3. So this will become e to the power 0 is to minus of 4.3 plus 0 plus c, or c is equal to minus of 4.3. Right, I think there is no error in this, minus 0. Yeah, c is equal to minus 4.3. Therefore, our solution will be y is equal to 1 oblique e to the power 2x square is to x plus c will be this minus 4.3, or x is equal to e to the power minus 2x square minus 4.3 e to the power minus 2x square, or e to the power minus 2x square x minus 4 oblique 3. This can also be written. Okay, this is the solution of the given problem, friends. We move to the next question now. In this question, friends, we will use variable separable methods, and maybe we need to do few substitutions to find the solution. So first of all, I'll write this as and segregate it along with the variables. Okay, and here I'll assume y is equal to sine theta. This will give me dy is equal to cos theta d theta. And substitute dy here and y at this place. We will have cos theta d theta oblique 1 minus sine square theta is equal to dx. This will become cos theta d theta oblique cos theta is equal to dx, or d theta is equal to dx. Now we will apply integration in this, and by applying integration we will simply get theta is equal to x plus a constant of integration c, and theta we will resubstitute back from here. So if we have assumed y is equal to sine theta, this will give us theta is equal to sine inverse of y. Therefore, we have sine inverse of y is equal to x plus c. Now, it says that the value of y at x is equal to 0 is this much. So I'll put sine inverse of oblique 1 square root of 2, and x will be 0 plus c. This will be c is equal to sine inverse of square root of 2 is how much we need to find. This is nothing but pi oblique 4. Therefore, we will have our equation as sine inverse of y is equal to x plus pi oblique 4, or we can write this y is equal to sine pi oblique 4 plus x. So friends, we have come to question number 24, and question number 24 looks to be little lengthy because we have to do a variable separable, and then there are some numbers which is going to create little bit of difficulty for us. Okay, so looking at this, actually we can do a variable separable method by writing y prime as dy oblique dx and taking this y this side. So this will become y cube minus half of y, or if we take y as a common, we will have y square minus half. This can also be fragmented into two portions, and it can be written as a square root of 2y minus a square root of 2. Now in case of variable separable, we will write all y portion with dy. I will write dy and then bring this into the denominator of this by writing it y plus and then dx will come this side and become dx here. Now just one more step is required for you to do in order to solve this, and the step is you have to do a partial fraction decomposition in order to separate these two. If I take 2 and y minus is equal to a oblique y plus b oblique plus c oblique y minus. I will not spend time on doing this partial fraction decomposition because I have done that in a previous question. I will simply write the answer that we get after doing it. We will have a is equal to minus 2, b is equal to c is equal to 1. Okay, so this thing which is given here can be rewritten as minus 2y plus 1 oblique dx. Okay, and then 2 dy oblique y plus dy oblique y plus 1 square root of 2 plus dy is equal to dx. Now what we have to do, we have to simply apply integration on both the sides, and we will if I put integration here, here and here, we get minus 2 of ln y plus this will be ln y plus square 1 oblique square root of 2. This will be plus ln y minus 1 oblique square root of 2, and this is x. And please do not forget to put a constant of integration c. Now we have to take it just little further. This is ln y to the power minus 2 plus ln y square minus half. This will plus will both be multiplied, and this can be written in totality as y square minus half divided by y square is equal to x plus c, and take an anti-log to get y square minus half divided by y square plus e to the power x plus c, or e to the power x is to e to the power c. Here e to the power c also remains a constant. We can write We can choose any other constant than c, and let us write this as a c1. So I can write it y square minus half is equal to y square c1 e to the power x. Okay, and bringing this entire portion here and taking this side of the equal sign, we get y square 1 minus c1 e to the power x is equal to half here. And now let us use what is given as an initial condition. Initial condition says that y is equal to 0 is 1 oblique 3, which means the value of y will be 1 oblique 3 when x is equal to 0. 1 oblique 3, this y square will become 1 oblique 9, and 1 minus c1 e to the power 0, and this will become half. 1 minus c1 is equal to 9 oblique 2, and c1 will be 1 minus 9 oblique 2 or minus 7 oblique 2. So we have to take this c1 and substitute here, and we get y is equal to, this minus will become plus because there is a minus, so this will be 1 plus 7 oblique 2 e to the power x is equal to half, or half is 2 divided by 2 plus 7 e to the power x. This will cancel each other out, and y will become plus minus of a square root of 1 oblique 2 plus 7 e to. So this is the answer of this problem. Let us go to the next question now. So we have come to question number 25 now. This is pretty simple. This is a variable separable question. I think you should not have any problem in solving this. So we have to take this secant of x with dx and secant of y with dy, and we will get this will be here one of the secant of x that we can directly write as cos x dx minus 1 oblique 3. Here 1 oblique secant of y will become cos of y. Apply integration on both the sides. This will be simply 3 sine of x plus 1 oblique 3 sine of y is equal to a constant of integration c. Now we can use the given initial value in order to find this constant c, and it says when x is equal to 0, y is also 0, which means 3 sine 0 plus 1 oblique 3 sine 0 is c. This will give c is equal to 0. Therefore, our solution for this will be 3 sine x plus 1 oblique 3 sine y is equal to 0. This is as simple as this. So let us move to the next question now. Question number 26 is given here. It is not very difficult. I would say this is quite easy to do. We have to do a variable separable here. Cos, we will bring this side and put it in the denominator of this fraction and write dy, and x we will take this side and put in the denominator with dx. Becomes pretty simple now. We know sine hyperbolic derivative is cos hx, cos hyperbolic derivative is sine hyperbolic x. Therefore, the integration will also be in the same way. Let me assume cos hyperbolic y is equal to t and apply a differentiation on this. The cos hyperbolic y, when differentiated with respect to y, will give us sine hyperbolic y dy, and this will be dt on this side. Now this can be replaced here. This can be replaced with t, and this can be replaced with this t. So we have dt oblique t is equal to dx oblique x. Apply integration on both the sides and we will have ln t is equal to ln x plus a constant of integration ln c, or ln t is equal to ln of cx, or t is equal to cx. Now we had assumed t is equal to cos of hyperbolic y here, so we can resubstitute back and write it cos of hyperbolic y is equal to cx. And what is the initial condition? Initial condition is at x is equal to 3, the value of y is 0. So here we can write cos hyperbolic 0 is equal to c is to 3. So here we have cos hyperbolic of 0 is 1 and this is 3c. This will give us nothing but c is equal to 1 oblique 3. Therefore our solution for this actually will be cos hyperbolic of y is equal to x oblique 3. Okay, this is the answer.